All right, let's do some representation theory. There's a storm outside, so you're going to hear thunder. Okay, so this one's not too bad. So let rho from G to GLV, some vector space B, and let's see, B irreducible. Obviously, it's a representation where G is any abelian group. So it doesn't have to have finite order. So fix some element G and G. We will apply Schur's lemma. What are we going to use? We're going to use rho 1 and rho 2 equal to rho. We have V1 and V2, both V for whatever V is. And here's the interesting thing. F is equal to rho G, or rho evaluated at G. I like to write rho sub G as Serre does. In class, my professor liked to write it rho G, but then you'd have like rho of G of V, and so you have all these parentheses going around, whereas I find rho G of V to be nicer because you don't have as many parentheses. Whatever you want to do, F is going to be rho of G. So, for any H and G, rho G of rho H is rho GH. Oh, there's the rain. And that's the same as rho HG, which is rho H of rho G. So thus, what does this mean? This means rho G is lambda G IV. I use I. Let's just use I because there's only one vector space here. So because rho G commutes with rho H, we can apply Schur's lemma, and so we know that rho G is what do you call it? An I something. Whatever. Serre has some fancy word for it, or I guess it wouldn't be Serre. It would be the guy who translated this to English. Although maybe there is a word in French. Whatever. Rho G is a constant times the identity map. So, for some constant lambda G, and remember, lambda G here is a scalar constant in the field on which V is defined. So if V is a vector field over a field capital F, then lambda G is a scalar element. It's just some element of this capital F. So so some constant lambda G. So for all G and G, and for all V and V, rho GV equals lambda G V. So now let W be a non-zero element of V. Is it possible that no such element exists? If this is the case, then what do we know? Isn't that? I think this is not allowed by the definition of an irreducible representation. Wow, it's really coming down. But anyways, this isn't going to be an issue. This choosing a non-zero element. Then span of this element W, this is the span in so W is an element of V, and then the span is you just take this element of V and you multiply it by values of this underlying field, capital F. So then span of W is a one-dimensional subspace of V which is stable under G. That's because, yeah, you just, if you have any element of V, and if you have like some like lambda V, and you run it through row G, then it's gonna come, or lambda W. If you have some constant lambda W, this is just going to give you lambda G, lambda W, which is going to be in the span of lambda G, no, the span of W, because the constant is just lambda G, lambda. So this is a subspace of V which is stable under G. So, let's see, what's the best way to do this? Dimension of V, I'm just going to say it, dimension of V must be equal to 1, because if it wasn't, then you could do, then we have a subspace which is stable under G, and so you could do a you could decompose this representation into a direct sum of two other representations. And that would contradict the fact that rho is an irreducible. So dimension of V equals 1, since rho is irreducible. And hence, degree of rho equals 1. And so there we go. We've completed this proof.